Hello, everybody. I am Monica Beckwith. I am a Java champion, as well as I do JVM performance at Microsoft. I've been working with the OpenJDK Hotspot VM for about 2 decades now. I started, from the hardware perspective, optimizing the JIT compiler and generated instruction set, and then quickly moved on to garbage collection and stuff like that. I worked at Oracle, Sun, and various other places, and I've gained a lot of experience on understanding how OpenJDK works on the underlying architecture. Today, I'm going to talk about enabling Java, and this is on a new platform that is Windows and ARM, and it's ARM 64-bit platform, and I'll walk you through our porting efforts. So let's get started. Here's a quick agenda. I will introduce OpenJDK and ARM64. I'll talk about our port, provide a little bit of background, and then timelines and some nuances that we picked up along the way. I'll talk about how for such efforts, such big development efforts, there needs to be a strong backbone of testing and benchmarking and CI. So I'll quickly cover those. I'll talk about the next steps, and then as time permits, I'll quickly run through a demo. As you can see, I only have 25 minutes and there's a lot to cover. So it won't be a marathon, it's going to be a sprint. So please stay with me. Introduction. Let's talk about OpenJDK project. So the JDK in OpenJDK stands for Java Development Kit. OpenJDK is a free and open source reference implementation of the Java Standard Edition. It's available via the GNU GPL version 2 with ClassPath exception license. Please go ahead and read about ClassPath exception. There's a link to Wikipedia entry on that. So here's the timeline, the OpenJDK timeline. So at Java 1, prior to 2006, Sun announced its intentions of open sourcing the JDK project. So it was the first thing that Sun open sourced in 2006 was the Java Hotspot virtual machine, which is as I will talk more about the JDK, that's kind of the heart of the JDK. In 2007, Sun did a little bit more than that. It kind of almost entirely open sourced the JDK and just holding a couple of pieces back. By 2010, we had 100% open development of the JDK available for anybody that wishes to participate. And let's talk about the community now. So as Sun was doing all these things, and by 2010, actually, Sun was acquired by Oracle as well. So as this was happening between Sun and Oracle, Red Hat signed the Sun Contributors Agreement. As anybody contributing to OpenJDK would know that we need to sign the OCA and OCTLA, and I'm pretty sure Martin covered that earlier in the keynote as well. And then Red Hat also signed the TCK. Then we had the Porters Group that was created, and Porters Group is really important because OpenJDK was tied to x86-64, which was a newer platform back then, and certain implementations. So the Porters Group actually extended the OpenJDK to different architectures and different operating systems. So that was a pretty milestone event. And if anybody remembers Apple JDK, but by 2010, Apple also joined the OpenJDK community. We also had IBM and SAP by then contributing to OpenJDK. In 2013, there was the new star that decided to come and join this OpenJDK community, and that star was Microsoft. And here, because I mentioned 2013 because this was a collaboration between Microsoft and Azure Systems to improve Java on Azure. So that's when the whole Java on Azure improvement started. And with that, I hope I provided enough background on the OpenJDK and OpenJDK community, and let's move on to ARM. So ARM is a RISC architecture. What that means is that there is reduced instruction set. And when you have a reduced instruction set computer, these instructions are highly optimized, okay? Many people may know x86-64, and that's called a CISC architecture. And CISC is complex instruction. So basically, the same instruction is fully packed to do lots of memory translations and or accesses and operations and everything. It's a packed instruction, very complex packed instruction. And these instructions in RISC architecture are just optimized to do the job. So the other advantage of RISC is the number of registers that are available for various purposes. We talked about stack allocation. Hotspot does have stack allocation. So earlier today, right, we talked about the optimization stack allocation. Hotspot does some kind of, if it does escape analysis and finds objects not to be able to escape, then it can allocate them on the registers. So an ARM architecture, for example, would be very beneficial for such optimizations. If there's one thing that I'd like you to take away from this slide, that would be the load store architecture. So, for example, when you're operating on an x86-64 architecture, you have this complex instruction set that does a lot of data processing, and it can directly access the memory. This is not possible on an ARM architecture. And what ARM does is follows a load store architecture. So basically, your memory is accessed, remember, via this highly optimized instruction. So these are called memory access instructions. And the way that works is that the data must be first loaded into the registers, and then you can do some manipulation, and then you can store it into a memory location as such. Okay. So an example, if I had to give you an assembly level instruction here, we have LDR, which means load, and then the register RT and address. There's various combinations of load where you can specify the bitness. Of course, you need the register size of data and the address. With that, let's talk about Arm64. And throughout this presentation, and actually in the wild, you will hear the terminologies Arm64 and AR64. AR64 is actually the new 64-bit ISA, the instruction set. And when we talk about Windows, we talk about ARM64 because there's no such thing as Windows on ARM64. It's Windows on ARM, and then we talk about ARM64 as the architecture, the ISA. So of course, when we talk about 64-bit, that's the ISA that we're talking about, which means that our ints, we have integer registers that are 64-bit wide, our data is 64-bit wide, and our pointer is 64-bit wide as well. The ARM64 is also known as V8, okay, ARM V8, and I'll talk more about the ISA and how it developed over time. The V8 is, of course, ARM, as many of us may know, is a weak memory model. But with the introduction of V8, we also got multiple copy atomicity. So before ARM64, before ARM V8, ARM V7 was around, and ARM V7 was not multiple copy atomic, which means it was only single copy atomic, which means that all threads were not guaranteed to see the writes at the same time. So with the V8, we get multiple copy atomicity, as well as, so what that means is to be able to ensure access ordering, we need to have barriers and fences. And I'll show you a quick example here shortly. And ARM already has these kind of instructions called data memory barriers, DMBs. ISB in this case I showed here because I'll give you an example of how we do the instruction cache flushing. But an ISB is an instruction synchronized barrier, and it's for flushing the CPU pipelines, the things like that, branch target and stuff like that. There's also something known as one-way barriers, and this is what release consistency model. So if you look at the memory models and you read about release consistency model, that's what one-way barriers adheres to. So ARM does provide that as well. And these are your load, acquire, store, release kind of pairs. And so I've shown LDARs, STLRs, and stuff like that. So please feel free to read more about that. Very, very interesting. It intrigued me a lot when I was working at ARM, and I'm thankful to be able to learn from the horse as well. Here is an example. So in our code base, we actually this is from our code base actually. And what we're doing here is that we are providing read, write, and full memory barriers. A full memory barrier has to give the memory order and has to be sequentially consistent. Please feel free to read more about sequential consistency and how we need to guarantee that with respect to our memory barriers. Now, moving on to ARM ISA and the third-party systems and how they came about. I am kind of restricting this particular slide to the systems that we used, and I want to show you the ISA story with respect to those systems. So if I did an Arm64 timeline here, I mentioned Arm64 started with V8, and we have in our test system, in our CI, we have an Emacs system. And Emacs system is actually by Ampere Computing. It's an Ampere Computing's product. Prior to EMAG, it was also called the XGene 3 and Skylark, and they were both Applied Micros products. Then came V8.1 ISA, and we do have a test system called ThunderX2. I call it a beast of a system. It's got 256 hardware threads, and ThunderX2 is Cavium Inc.'s product. Now, Cavium Inc. has been acquired by Marvell Technology Group. With V8.2, we have a very own Surface Pro X's. There are two different processors, SQ1 and SQ2, and Surface Pro X's are Microsoft and Qualcomm's collaboration. So these are the test systems that we used in our test CI pipeline as well. And now we are at 8.3 plus, and there are various systems that have been announced and are going to be announced soon. So that's a quick overview of our test systems and how they came about and why we chose them. So we chose one from each of those incrementally things that are available. Quickly jumping into a port, we'll have some background there. We'll have some nuances that I'll cover, and our timeline, which is the best part of this presentation, because there are various cameos. Okay, so why OpenJDK port? What is a port, right? We all know Java to be write once, run anywhere. But when you have a new platform, and I mentioned about the Porters group earlier, remember back in 2007 when this whole thing started, the whole effort was to bring Java onto new platforms. So Windows and Arm64 is a new platform for OpenJDK. And to be able to get developers to develop in Java, we need to make sure that the JDK is available, right? The second thing we want to make sure is that even if you're not developing on the JDK, you still have a runtime environment for Java. So you could run your apps on the Windows and ARM platform. So we need the JRE, which is the runtime environment for Java. So let's look at a JRE. The JRE consists of the Java Hotspot VM, as well as some class libraries. The Hotspot VM itself is divided into like the runtime area, as well as the execution engine. And the class libraries, as many of you know already, is the UI toolkit, as well as the base, lang, util. We all use this the libraries. Now, a JDK is a superset of the JRE. So JDK enables a developer to be able to utilize tools and utilities to be able to develop and debug their applications. Okay. Let's dive into Hotspot. Okay. The way I want to talk about Hotspot is with respect to the code base, and because that's how we, like, if anybody is interested in importing OpenJDK, that's where you would start. So the Hotspot source repo is very nicely arranged, and kudos goes to Oracle for cleaning it up, and with all these kind of modular development efforts, it's really, really easy to understand each component. So most of the code, as you may already have imagined, is non-OS and non-ARC specific. And this would be your memory management stuff. So your garbage collection, your allocations, your compiler work stuff, and metadata, etc. Then comes like more specific to either the CPU and the OS, etc., etc. So the rest of the code is organized as such. You have architectural specific code. For example, we are dealing with ARM architecture, so you would have the Arm64. Previously, there's already code for x86, so on and so forth. Then you'll find the OS directory where OS-specific code resides. We have Windows because we're working with Windows and ARM, and of course there's Linux, etc. Finally comes the big chunk where you have OS and architecture-specific code, which is in the OS_CPU directory. This is where most of our work was. It was in the Windows AR64 directory. And of course, most of our work is inspired. And big thanks and shout out to Red Hat for all the effort that they have done in importing Java to Linux and ARM. And we have been working with them hand to hand and building on their work. So thank you again for all the collaboration. Now I want to dive into the runtime. So I mentioned that Hotspot is runtime and execution engine. And the runtime is basically, it has one goal. The goal is to convert bytecode to native code. And you may know the interpreter is the runtime, right? But there's also a lot of other things that is done by the runtime, which is like class loading, bytecode verification, thread management, synchronization, yada, yada, yada. Our changes were basically to get the JDK launcher, which is used for JVM creation and destruction, to use the structured exception handling on Windows. What about the execution engine? This is the heart, right? This is where your compilation, your memory management unit, everything resides here. So to provide a quick background on compilation, we have in Hotspot, we have C1 and C2 compilers. C1 is your client-side compiler, and your C2 is your server-side compiler. And then we have this tiered compilation that starts from C1, goes to C2 with profile-guided optimizations and everything. So for our work, most of our changes were in the execution engine, as you would have guessed. We wanted to make sure that Hotspot understands Windows and Arm64 specific changes, as well as, remember I talked about Linux and Arm port that already existed. We want to make sure that that was able to understand, if there's something that's Arm64 specific, we want to make sure that it understands and speaks Windows as well. Okay. Now let's dive into our learnings. I'll start with something simple. So Windows and ARM specific running. What we learned is that there are some special platform registers that we have to be aware of. And that's important because these registers have special meaning for user and kernel modes. And what we have to do is make sure that we treat it as reserved and non-allocatable. So we cannot use them basically. This is not a problem on Linux, but on Windows as well as on Mac OS, which is where we took these learnings and applied it to Mac OS as well. We have used it now as reserved. Okay. The other thing, remember I talked about ISBs. So there are instructions for invalidating instruction cache, and we used a function in MSVC, which was from the MSVC API, and this is how it looked here, right here. So we use the flush instruction cache right here. Let me use a laser pointer. There you go. Flush instruction cache function right here, and then we provided the bytes and size and everything. So yeah, so MSVC was very useful in there. So that's a Windows specific thing I wanted to highlight here. There's one more thing. As you may know, once you know what platform you're running on, it's very easy to put in some optimizations. These optimizations that were put in were in the form of hand-coded routines, and these are assembly routines. For hotspot, we call them assembly stubs or just stubs. So we did that for byte swaps and copy stubs and stuff like that. So these are optimized routines. Also, we made use of Windows API for detecting CPU features such as AES and CRC32. And here's an example right here. So if you see is processor feature present, that's the function, and then we ask for different features as shown here. And let's go into MSVC level details. MSVC provides a lot of intrinsics that we could use. I already mentioned about the standard atomic intrinsic that we used for read-write barriers. Those standard atomic stuff, they use MSVC intrinsics underneath it all. So of course we wanted to make use of that. There's also things like special intrinsics that MSVC offers. And I'll provide an example here, no-op, like no operation. And as you can see, if it's GNU, we use the ASM volatile as well, and no-op. But for Windows MSVC, we use the intrinsic right here. The best part of our learning, and of course we encountered this at the very beginning, there is this concept of LP64 versus LLP64. That's a data. These are different data models. And if you want to read more about it, of course, I've linked a Wikipedia article here. And if I want to summarize it very quickly, so it's basically when you want to extend 64-bit long integers and pointers to 64-bit long integers and pointers, which are explicitly needed by the 64-bit Windows platform. So let's look at the data model here quickly. So as you can see in red, I have shown how long on LP64 is 64-bit, but on LLP64 it translates to 32-bit. But long on both LP64 and LLP64 data models translate to 64 bits. So why this is important? Because remember I talked about the existing code base on Linux and Arm64. So most Unix-like systems follow the LP64 model. But lucky us, Windows follows the LLP64 model. So of course we had to make sure that we are accommodating all longs as long so that we don't do the bitness errors right there. Now the fun begins. Let's look at the timelines. Okay. So that's me. I started looking at the port and investigating and putting in Windows and Arm64 level code base into towards the end of January, early February. And this was mostly partial, but I had the support of an Emacs system. Emacs system kind of helped me get through basic things, and I was able to produce Java version, and of course a crash dump, a core dump right after. By March, I also had Ludovic join the team, and Ludovic helped a great bit with the CI, so working with the infra team. Also, by that time, we started collaborating with the MSVC team, trying to understand how we can utilize intrinsics, etc. And of course, I mentioned about the CI, and we started working with JDReg, which is the test harness. Internally, we also started kind of co-opting these benchmarks and making subsets of it so we can run it every time we make some changes and get quick numbers or core dumps, depending on how lucky we are that day. By mid-April, we had our ThunderX 2 and our Surface Pro X systems as well. And it seems like I'm almost out of time here. I'm going to just quickly go through. So we started with C1, enabling C1. Remember the client-side compiler and parallel GC We had some Windows-specific core count issues. We enabled that as well. We made sure C2 is functional and then made some more benchmark level changes in JNI code and everything. Bernard joined our team. Bernard helped with the G1GC bug, and our first patches first surfaced on OpenJDK. And with the help of OpenJDK community, big shout out to Oracle and Red Hat, we went from JEP drafted to getting integrated into OpenJDK by October 2020. So we are now going to be with, when JDK 16 comes out, we'll be there. I hope you take us for a test ride. Here's the testing CI. So please feel free to browse the slides later at your convenience. Next steps for us, we want to keep on keeping the port up to date. We want to make sure that we work closely with the Windows as well as MSVC teams. I talked about the Apple Silicon and Mac OS port. We want to keep doing that. Here's a work that we have done with respect to CI and AOT, and of course, backport, all these to JDK 11 update. I may not have a quick time for a demo, or maybe I could do that. Let's try that here. This is a demo at a fast speed. Apologies right there. So here you can see that it's a code, this simple, we're just looking for the simple string right there. And then of course, this is showing you it's a Surface Pro X right here. And now we do the Java version. That's the build that we worked on right here. It's a Windows and Arm64. And we'll go and open localhost here shortly. And of course, you see the string right there. And that's it for the demo. Thank you all. I apologize for running out of time. There's links to the GitHub repo, our PR, a few announcements that were there, and of course, download it, work with it, send us feedback. Thank you very much. I appreciate your time.
Thank you so much, Monica. I think there was one cool demo. I'm not sure if you can pull this off in 30 seconds. The Java Swing demo app. Can you do that? Oh, you're muted. You got muted, Monica.
Oh, I'm sorry. Yeah, so I have to connect to my thing. This is where I just had linked it together, so I just stuffed it in a recording.
So never mind. So never mind for today. But we did post a picture of the Java Swing demo suite when we released the first binary or the second binary that had the Swing support. So it's quite impressive that he, I think, throughout the time, I mean, it was a long project given the timeline that you showed us. But I do believe that the amount of hours was not that much, right? In terms of like it wasn't like 15,000 hours to develop this thing. I think the work that Red Hat did with the port for Linux on ARM and other engineers and other companies really contributed to making this port so quickly implemented, right? Given the reality of longer projects that we've seen in the past.
I agree. I mean, we were working with giants. You know, just built everything on their shoulders, and they were very helpful. So things like, you know, how should we test it? How should we test it so the OpenJDK community understands that those kind of hints were provided to us by Red Hat as well. So not just like the technical strength of this port, but also the ability to be able to get merged in, you know, doing the incremental patches, the test systems, you know, making sure we're covering all grounds of existing architectures that we may have touched or modified. So things like that, and of course Oracle. Like at every PR we put out, every incremental patch that we had out there, we had support from Oracle in saying that, hey, have you looked at this? Or yeah, this is great, and let's just push it through and all this fun stuff. So we had a staging repo where we actually pushed everything first in the ARM64. That's when I talked about we became committers to the ARM64 repo. I mean, this is all, it seems like it's only long because we made sure that we were meticulous in our testing, in our CI and everything, because we didn't want to put something out there that we haven't tested and worked with. And that's what we do. That build platforms are, I mean, Bernard will tell you stories about how he uses Surface Pro X. And come join us at AMA tomorrow and ask Bernard more questions, of course. So
awesome.
Yeah.
So we have the AMA tomorrow, and you're gonna be back for the AMA with Bernard, and then we can continue the conversation on Windows on ARM for sure.